will show that it is recording. Let's see. Yeah, it is showing that it's recording. Yeah, so I got from my other this thing also the message that it is recording. Okay. So these three pictures, yeah, somebody was talking. Yeah, can you tell me what are these three pictures linked to? So it looks like in a barren land there is some warehouse kind of thing, and you all know this is. So I got one answer probably. No, okay. So these are this is the Wright Brothers cycle shop, where in Dayton, where they actually did all the analysis and then all the manufacturing or making of this thing. Please, Aditya, please mute yourself. Okay, so if you see that they had a cycle shop, and in which after which they started working on this aircraft, and this is the Wright brothers, and we all know that they are considered the like pioneer in terms of the flying with the human being. So the first flight with the engine with their gliders is this is the picture that you see. But the story behind this Wright brothers is very encouraging, and this is where I actually this is why I tell this story, and this is where I think the motivation should come when you are trying to do something new or something challenging. If you think that okay, they had just a cycle shop, but they started this design of this aircraft based on the theory of Lilienthal and Langley. So Langley and Lilienthal as before in 1800, inviscid theory was developed quite substantially, and based on that you can actually estimate the lift that is generated by aerofoil, and they use those theories, and they developed their first model. And in 1901 they were so frustrated when they did their first flight, and they saw that the actual lift that they are getting is 1/3 of the lift that they predicted using this Lilienthal data and all. So they were so frustrated, they failed in their test, and they built it and they thought they will fly. They said that while they were returning to Dayton, they said that 1,000 years nobody is going to fly. That is Wright brothers statement. Okay. So they themselves said in 1901 that 1,000 years nobody is going to fly, but they did not leave it there. They came back and they said, okay, let us find out what is wrong with this our model that we have made. So they built a wind tunnel, and so it's a very elementary wind tunnel today's with respect to today's wind tunnel that you see. It has a fan and it has a test section, and you can see that they mount the model using these things. Can somebody guess how many models they tested in a 1 year time, because they flew after 1 year, successfully flew after 1 year?
50.
50. Okay, in 1 year, 365 days, 50. Anybody? Any other guess? That's a reasonable guess, at least.
100.
If somebody is, yeah, if somebody is very efficient today, also, if you want to make model, when you will be working, you will see model making and then testing how much time it takes one model. So in this period, they made about 200 plus model in 365 days and tested those models. And they figured out what is the problem. But at that time, 1901, today you will get all modern instrument. You put the model, you put a force transducer inside the model. It will give you all three component of forces and moments and three component of moments. So it will get all force moment, everything you can measure how much this wing is generating. That time you did not had this kind of transducer available, nothing available. So what they had is their cycle shop. So what they did, this I'm not going to read. I'm just going to, you can read it later. So what they did, they created balance based on this, using this cycle spoke and different weights. So balance you have seen all in the shops. Today you see all digital balance, but even today if you go to market in the sabjialas, you will be using the conventional balance. So, but they created the balance to measure both lift and drag using the cycle spokes and other this thing, some link they created using that. And this is that balance they used to mount the model, and they measured the lift and drag. Okay, and you can see there is a dial through which they can measure the lift and drag. So that also they created first, and then they tested. So within that 1 year, they tested about 200 models, and then they figured out that what was their problem in their model. And can anybody have any idea what was the model? What they figured out in their problem in their model? Okay, so you should read actually a little bit of history of aerospace, because that gives a lot of motivations. And Anderson book, you will see there are many historical notes available. And today with Google, you can actually find lots of things that was difficult in earlier days when we were student, but today you will have a lot of access. So you can actually read, and you will see many interesting stories are there. So the primary thing that they figured out is that the model they were using, the span of that, the length of that wing was small compared to what they should have taken for the chord that they have used. That means the chord of the aerofoil that they have considered. So they had to increase that aspect ratio, that is length by chord, and they realized that what aspect ratio they were using, that was not producing sufficient lift. Whereas if they use longer aspect ratio, then they will produce sufficient lift. Now, what is the link between the longer and shorter? What is the difference that it can create? Can somebody point me out? Let's have the class a little more interactive. This is introduction class, and it is more about the familiarization of aerospace and aerodynamic structures, propulsion, and flight dynamics. So can somebody answer?
So increasing the span might increase the stability of the aircraft.
Okay, so anything else? Think little more basic.
So it will increase the lift as more area will be exposed to the
Okay,
foil.
I'm talking about here. So lift per unit area, because when they calculated the lift based on the theory, and they made their model, they realize it is producing 1/3 of the lift. So this is what I said. And now when they increase the model, when they measured, they said that they realized that if the length of the model they increase, that means span of the wing they increase, then it actually produces the lift that they expect, close to that from the theory. So what could be the difference between theory and this experiment, when we are seeing that smaller span is actually producing less lift and longer span is actually producing more lift, or more closer to what theory is predicting? So these theories that you see in developed, most of them are two-dimensional theory. When you talk about the two-dimensional, that means you assume the wing is an infinite wing, and if you take if it is infinite span, and then you take a section, then you will find that the lift in that section per unit span will be what theory will be giving. You use that and you start building your model, but your model will have a finite dimension of the wing. Now, yes.
I'm not able to understand how they are getting lift from this design.
Lift
Not able
will,
to understand that design.
yeah, lift we will discuss. We are not discussing how they are getting lift. Okay, what I said is just two-dimensional theory predicts that this much lift force will generate per unit span, means per unit length of the wing. Okay, but when they are using a smaller wing aspect ratio or smaller length, what will happen? It is not two-dimensional. Two-dimensional and three-dimensional, I hope you have that idea. Two-dimensional means we are talking about the wing, which is like, if I consider this this my notes, this is a three-dimensional body. It has a finite thing. If I extend this length to infinity in both sides, then this will be a two-dimensional body. Okay, if I think of a one-dimensional body, then this dimension will not be there. This dimension will be small. It is just a infinite line. So same way, so they were taking a finite wing, but now once you take the finite wing, the three-dimensional effect will become important, because from the wing tip, you have seen the tip vortex in the previous day. So the finite wing means the three-dimensional effect becomes important. Yeah, please. Yeah, if you have a question. Okay, so now, so they figured out from these series of experiments that they should use a much longer wing, so that when you take a longer wing, then your major part of the wing, the forces that will be produced will be matching with the three-dimensional part, two-dimensional theory, because three-dimensional part is now excluded more or less. So that is why that is the findings they had from these experiments. And finally, with that, within 1 year, which they predicted that 1,000 years nobody going to fly, they because the effort they had put and it did not fly. So within 1 year, they could fly their model. So they obviously built the engine and other things, everything. So you can go and see in the details. This is their flying and this thing. So from this story, you understand that the failure that they had and the effort they had, and then after the failure, if they would have just left it and they went back to their cycle shop, definitely, but that was still there in their mind, and they built it successfully, and that's why they are in the history today as the pioneers of the aeroplanes, modern days aeroplane. Okay, so so this I'll just skip it right now. When we'll come to other things we'll talk about. So modern day aeroplane looks much different than what Wright brothers started. And when we talk about this aeroplane, then we have to talk about why this wing is there, and how this wing generate the lift and thrust. To start this, we need some basics background of aerodynamics, and we'll come to that, and that is what we'll be talking next. And so how many of you have done any course on you are doing the aerodynamics 1 course right now, is it?
No, sir. This is our first introduction. We are doing a fluids dynamics course.
Oh, okay. You are doing the fluid ESO 204 course, that is fluid dynamics course.
Yes, sir.
Okay, okay.
Yes.
So right now you are doing fluid dynamics course. So I am sure some of this introduction that I am going to talk today, because I am not going to talk in very detail. I am going to talk today is just that related to fluid dynamics. And once we do that, then what is this forces, how these forces are generated. There is a pitching motion, rolling motion, and young motion. So that is, the aircraft can roll with respect to this. It can pitch and nose down and nose up. That is the pitching motion. And it can also rotate in a horizontal plane. So that's the yawing motion. And then how wings and different control surfaces will be generating forces. All these things will be little clear once you have some fluid dynamics background, and which I don't know how much is covered. So I will just quickly go through some little background so that I can explain you all this in details. So today's class will continue with that background. So I'm sure when we are talking about this aerodynamics or fluid dynamics, we need to talk about what is fluid and how do you define this? Because if I start looking at air as a gas, then you may think that we should start analyzing this using each molecules of the gas and molecular level. We should start analyzing this. Now that is where I think the first thing that we should understand is how do you define a fluid particle, in a sense when you are saying that velocity at a point, or you are saying the pressure at a point over any of the surfaces, then what does it mean? Okay, and or when you are talking about density at a point, because we are aerodynamics people, we have to think about the both density changing flow also, because when there is a flow with very high speed, high Mach numbers, then you will see density variations are important. So we need to define what is continuum and how do we define a fluid particle. So to do that, so this has been already probably discussed in fluid dynamics course. And if you,
Yes, sir.
yes, sir. Okay, so if it has been discussed, then I will discuss very briefly and quickly. So if you see the gas as a collection of molecules, and if I just take a very small control volume under microscope, we are seeing this gas, and if I take a very small control volume, the number of molecules present in this volume with time, you will see sometime there are few and sometimes there may be no, or sometimes there may be more. So it will be density, if is defined by density is always defined by mass per unit volume. So the number of molecules present, mass of them, and delta m by delta v, the volume that I have taken, that will be defined as density. And if it is very small, then you will see the number of molecules are varying substantially, and you will get a fluctuating density. If you increase that volume little bit, then that fluctuation will decrease. That means the density variations at different time in that volume will be changing. Or if you make this same volume, if you take at different locations, it will be fluctuations will be changing. And then if you take a sufficiently large volume, it is still under microscope, it is sufficiently large volume, then you will see number of molecules present in this volume at any instant of time is constant. If you can identify that volume, then that is the volume in which you can define. Let's say if I am defining density is the volume delta V star, delta m by delta V, where delta V star is the volume, that critical volume for in which the number of molecules that are coming in and going out due to their random molecular motions will remain same in that volume. So this critical volume is how much? Can somebody tell me? So what will be the logic behind determining this critical volume? So beyond this critical volume, if I continue, if I increase the volume, it remains constant. This density will remain constant. So this uncertainty is called microscopic uncertainty, and this is macroscopic region in which we can actually, because our physical dimensions of any measuring devices should be small, but it should be still large enough. If I considering it should be away from microscopic uncertainty region. So how small is this delta V star? Okay, it is already written, it is 10 to the power minus 18 meter cube. Okay, so if you see 1 micrometer cube, that is 10 to the power minus 18 meter cube air, it contains about 10 to the power 7 molecules. Okay, and so it's a large number of molecules. And so number of molecules coming in and going out from this, so this delta V star not actually 10 to the power minus 18 meter cube. This I am talking about 1 micrometer means this much. But what will be the delta V star? Can anybody tell me from any physical argument or physics of this understanding? So now Molecules are, as you could not say, I just wanted to discuss this point only. As molecules are, somebody responded, critical. Yes, that is a critical volume, but how much is that volume? Okay. So now molecules are in random motion. And if I bring in the mean free path, then mean free path is the, you all know that average distance these molecules travel before collision with another molecule. So if I take a cube of lambda, mean free path is lambda of air, it will contain about 15,000 molecules, large enough. And you will see the fluctuation in density for this cube of lambda is almost negligible, 0.8%. If I had taken smaller than that 0.1 lambda, it will be much larger, 25% will be the fluctuation in density that you will be measuring with the uncertainty, the microscopic uncertainty you are seeing. So why the lambda is becomes a thing, volume, lambda cube becomes a volume in which the this fluctuations is so less, because mean free path is what? Average distance that they are moving before collision with another molecule. So if we now start thinking of probability of number of molecule present in any of these volumes that we are considering, any of these volumes, probability that number of molecule present in this or number of molecule coming in inside this volume and going out from this volume, that is what will determine how many molecules are present here. So if I take a lambda cube, then the probability of number of molecules going out of this volume and number of molecules coming inside this volume is almost same. Okay. And as a result, this lambda q is your actually delta v star. Your delta v star is not this, delta v star is lambda q. Okay. So that is what is important, that this is the minimum volume that if you consider, then you will be in the macroscopic zone. Okay. Now, so with this macroscopic zone, now we have defined a small volume which is lambda q, or maybe more than lambda q, but it is still sufficiently small so that I can take a tip of a pen or tip of a point, and I can say that I can define all the fluid properties there in the macroscopic sense. So entire analysis that we do, most of these studies in our aerospace is in the macroscopic zone. But if you go to the outer atmosphere or the upper atmosphere where the air is very thin, your spacecraft dimension may be of the order of mean free path. Okay. In that case, you have to do molecular simulation, not in the macroscopic sense, whatever we do that. So in that case, you have to use either kinetic theory of gas or the molecular level simulation to understand what is happening in the flow. But once we are in the macroscopic region, still delta V star is sufficiently small. So I can take one point and adjacent point. This is a large view. And I can define the properties at every point in this space. And I can join a continuous function like this. And I can say this property rho is a function of space, as well as it can be function of time at any point. Okay. So that is why we can apply the properties of continuous function in the continuum model. And this is what we will be doing in entire macroscopic analysis. This properties of continuous function will be using, and that's why we call it about continuum. Okay. So similarly, we can define the velocity of a fluid particle. So velocity will be the number of velocity will be defined as a momentum by mass. So total momentum of the molecules contained in delta V star by total mass of the molecules present in that volume. We can define stress similarly. Stress is defined force per unit area. So you can define delta F by delta A, where delta A tends to delta A star is defined as a stress. In fluid, in aerodynamics or fluid dynamics, whenever we are talking about the stress, usually we decompose into two components. One is normal to the surface and another is tangential to the surface. So tangential stress is tau, and normal stress, when we write it as a stress, we write it as sigma usually, or sigma n, whatever. but direction of that normal stress you will be taking is always outward normal to the surface, because any surface or any area is actually a vector. It has a magnitude and it has a direction, and direction of that area is its outward normal. So normal stress, when we say, it will be outward normal, and that will be normal to the surface. But whenever we say pressure, pressure is actually opposite to the normal stress. It is inward to the surface. Okay. So this nomenclature you should be familiar with, that pressure means it is always acting towards the surface. Okay. While we are talking about the stress convention is stress is acting normal to the surface for the normal, and tangential will be in the tangential direction. So now you also have defined fluid, and you can define fluid how. Air is also a fluid, remember. Air, all liquids and gases are considered as fluid. And so if I consider, let's say, a solid object, like let's say this, in the class I would have taken a chalk, and if I have twisted it, if I apply a torque, then this will just have some internal strain or deformation, and then it will reach an equilibrium position depending on the torque. If it would have been a chalk, and if I had to increase the torque, at some point it would have been yielded, once it would have been just ruptured, it would have broken, the chalk will be broken. So, but up to certain torque it will withstand, and when it is withstanding this torque, at that time it is reaching another equilibrium by developing some internal strain, because this torque is applied here, and the stress is proportional to strain that we know in this case of solid. The difference between solid and fluid is, in fluid, let's say I have this arrangement. If you see, let's say this is a rotating drum, which is in a table which is rotating at some RPM, and this is a fixed cylinder which is immersed into it. Now, when I rotate it, what will happen? The fluid will also rotate, and if we rotate it for very long time, sufficiently long time, then all the particles will be in an equilibrium steady state, and you will have at any point you will have V theta will be equal to omega r. Okay, the velocity at tangential direction will be V theta is equal to omega r. Now let's say torque is T1, okay, and corresponding omega is the particles angular velocity, omega is omega 1. If I increase the torque, okay, T2, which is greater than T1, then what will happen in the same point? Can somebody tell? This omega 1 will increase. So now corresponding omega 2 has changed. So now one equilibrium state we have, where we have corresponding to the torque, all the particles are moving with some omega 1 that is corresponding to this rotational thing, circular frequency. And now if I increase the torque to T2, it will all, so if I move the drum faster, then it will have another rotational speed omega 2. So as a result, in this case, the equilibrium state is what? The tangential velocity, if you think of, it is the displacement per unit time. So in this case, stress was proportional to strain. Here it will be proportional to rate of strain. Okay. So that's what you are seeing, the displacement per unit time is your velocity, and you are seeing this tangential velocity change corresponding to this torque change. So it is, so under shear, it will start deforming and it will reach to an equilibrium state, okay, such that your rate of strain is proportional to stress. So that's the difference between fluid and solid, where rate of deformation is important in a fluid. So when you, in this fluid mechanics course, you will learn that when stress is proportional to strain in a solid, in case of a fluid, it will be proportional to strain rate, and so, okay. So this is, so today, now what we have defined a fluid particle, and we have defined what is fluid. in terms of in comparison with the what is solid, and we have said what is fluid. So otherwise we say fluid is any gas and liquid is fluid, but in terms of the property, in terms of stress strains, you see a stress strain rate equilibrium in case of a fluid. Okay, so now once we know the fluid, we just go to, just a second, I am not in the top of it. I just quickly talk about the kinematics. So can somebody tell me what is the difference between kinematics and dynamics?
Dynamics also studies the cause of motion, while kinematics studies motion.
Yeah, great. So kinematics means when we are talking about the kinematics is the study of how things moves. That means the study of motion. And when we try to answer why it is moving, the nature of forces that is causing the motion, then it is dynamics. Okay. So again, kinematics means we are talking about the displacement, velocity, acceleration. These are the motion related quantities. Whereas dynamics means the force that is acting, force is equal to mass into acceleration, then that force is, as you consider, it will be dynamics. Now, when you consider, I'll go through this very quickly. When you consider solids, because this probably has been taught there. So if I consider this slider crank mechanism, if I rotate this wheel with some motor corresponding to this, depending on these links, I will get a amplitude and frequency. Frequency will be similar to the rotational frequency of this motor, and I can generate a sliding oscillating block of this block D here in using this mechanism. So now this oscillation, how much it will oscillation depend on this link lengths, and what will be the frequency of oscillation, that will depend on this rotational frequency. So we can determine this very easily. In case of fluid, can we do those similar thing? In case of fluid, we cannot do similar thing, because even if I consider a series of particles and think this is a link and that is a link, in any moment, all the time the fluid particles are deforming. Okay. Hence, such kind of simple solid motion will not be possible, because fluid particles are not rigid, they deform. Okay. So what happens in case of a fluid motion? Let's say take a very simple example. Let's take a water in a drum and it's flowing through an exit. Okay. Now, I can try to argue, let's say, if I take the this is like a chain of fluid particles along this line, and I can argue that, okay, this fluid particle is moving this much distance in over a time, and in same time this fluid particle will also move this much distance. Does it happen in that fashion?
No, sir.
No, that will not happen. If it would have been a thread, then obviously the thread, how much it moves here, same amount of a thread it will move here. But fluid, it does not happen, because this similar to the solid, these things will not happen here. But what will happen? There also some constraint will be there. And what is the constraint here? The constraint is the amount of mass that is going out. Same amount of mass will be such that this volume will decrease by the same amount. So if the density is constant, that amount of fluid that is going out, the volume of the fluid, same amount, same volume of this thing, height will come down such that this volume and that volume is same, which is that is nothing but your conservation of mass. So that is a constraint, which is conservation of mass, that is doing a similar thing here. So you can see that kinematics, when you are talking about the fluid and solid, the fluid is much more difficult, because we cannot consider each fluid particle and take like that so easily. So then there comes the Lagrangian or Eulendian description of the fluid motion. So this has been taught already. So some of you may not be there in that fluid mechanics course. So let me just very quickly discuss that today before I end. So what is Lagrangian description of fluid motion? In Lagrangian description of fluid motion, you are describing the motion of a rigid body, like a rigid body, let's say satellite moving around the earth, or motion of aeroplane with respect to a reference frame which is fixed. Okay. So now if I am taking this with respect to the reference frame, let's say this is one particle and I identify that particle by its initial position R0, and I track this particle as it moves with time. So at any other time, so at t is equal to t0, it is at R0, and at t is equal to t another time, it is at R. Okay, so I can define the R of this identified particle. Remember, this is not a variable like t. This is just a identifier. That's why I have used this semicolon. So this identifier indicates that I have identified this particle, and its position I can track with time as R is equal to R of R0 t. Okay, so R is the position vector, because as soon as we are talking about the position with respect to this reference frame, it has a direction, so I can talk about as a position vector. And this position vector of the particle with respect to, now we are considering this fixed frame of reference, or the inertial frame of reference. In that means inertial frame and non-inertial frame, all of you are familiar with. Non-inertial frame example will be accelerating frame of reference, and for aerospace, non-inertial frame of reference is very important. And I think in this fluid dynamics equations, when you will be deriving in ESO course, maybe the non-inertial frame of reference, those equations will be derived. Otherwise, our aerodynamics 1 course, I am sure it will be derived. Because if you see the helicopter motion, or if you see flapping wing motion, or if you see accelerating rocket, those are not a inertial frame. These are non-inertial frame of reference. Okay. So in Cartesian coordinate, this will be the x, y, z will be this. And so x0, y0, z0 is corresponding to R0. And we are writing this t. So R as a position vector with respect to this coordinate, you can write x, y, z, I, x, j, y, k, z. I, j, k are unit vectors along x, y, z direction. And we can write velocity is equal to dr dt, and acceleration is equal to dv dt or d2r dt. So position R, velocity, acceleration, all I can determine in this Lagrangian sense of description, where I can identify a fluid particle and it find its velocity and acceleration easily. If it would have been a dynamics, then you would have looked into the forces equal to mass into acceleration, which we are not considering in this kinematic analysis when we are considering, obviously, because we are doing a kinematic analysis. Now, alternately, now if you, let's say, consider the flow past this aircraft, and if you have to identify each of these particles' motions and then their dynamics, then it would have been enormous job, because you have seen the dimension of the fluid particles, and identifying all of them and their motions, and link to that with the what forces or pressure generating over the surfaces and all these things. Why forces and pressure are important? Obviously, forces are important for our flying vehicle because we need to generate sufficient lift. Okay, the lift force, that is vertical force. And when it is flying, our engines that we are using, that should generate the sufficient thrust to overcome this drag of this. So forces are important, and pressures are important. Why? Because you have made with some structure this body, and somewhere the pressure is so large that your material with which you have made it, it cracks. Then it is a problem. So the pressures are also, the stresses that is acting on the body, that are also important. Now, finding all these particles that are moving over the surface, and based on that finding this information, will be much difficult. So instead of that, Euler said that if we can identify a fixed space, now we have identified a fixed space, and at any point I can say that the property, let's say density, is changing with time, and it is also changing from different point to different point. Now, the difference between the Lagrangian or Eulerian is, now we are identifying a fixed position in the space. So in our required important zone, so over the aerofoil, this is the cross section of this aerofoil wing. So this is the aerofoil. We will be talking about this aerofoil later. And in this, our zone of interest, I identify my zone of interest, and every point I find the variation of the property with time. So that means in this case, the velocity, if it's the property, it is also varying with the space and it is also varying with time. However, at this point space, whatever fluid particle is occupying, next instant of time in the same space, same fluid particle is not there. That fluid particle might have moved here and another fluid particle might have come here. Okay. So as a result, you cannot, when you describe the flow using Eulerian, you cannot actually straight away use force is equal to mass into acceleration, because when you write force is equal to mass into acceleration, this is the mass of the identified fluid particle, okay, or identified body. So if now the fluid particle, when you are talking about, now the particle has gone from here, we are talking about the let's say acceleration at this particular point. So that's why we need to find out the relation between this Lagrangian and Eulerian. So in Eulerian thing, we defined u as a function of x, y, z and time. It is not an identifier anymore. It is just a function of x, y, z and time. So let us consider how do we link this two quickly. We have 2 minutes time. So let's take a particle at density rho, and it has moved at time delta t to rho, and its density is now rho plus d rho. So what will be its change in density derivative d rho dt? D rho dt will be rho plus delta rho minus rho by delta t, isn't it? So d rho is the density change in terms of Lagrangian sense, and d rho dt will be Lagrangian derivative of this particle. But now I have defined rho as a function of x, y, z and t, and that particle identification is not there. So we can use chain rule of partial differential equation, that d rho is equal to del rho del x dx, del rho del y dy, del rho del dz, and del rho del t dt. This is just for any function f x, y, z, t, we can write this chain rule of partial differential equation. All of you are familiar with it. All of you have done maths courses. And so this term I can write is as this dot product of this and this, because you can see this dot product will give me del rho del x dx, del rho del y dy, and del rho del z dz. And I have del rho del t dt, which is function of x, y, z. Sorry, which is, when I am saying del rho del t, what is the difference of this del rho del t? Del rho del t means, by definition of partial differentiation, this means when we are keeping x, y, z constant, that means we are looking at the density variation at this particular location with time. We are not moving with the particle like in Lagrangian sense. So this is the local rate of change of density with time. So, and this can be written as del rho dot, this is dr, and dr is v dt. So I can write this is equal to del rho del t plus v dot del rho dt. So this now dt you take in this side. So d rho dt, which is in the Lagrangian sense, the rate of change of density, or a material rate of change of density. That means when you are following this material particle or fluid particle, this is the Lagrangian derivative or material derivative, is equal to, when you are defining something in the Eulerian sense, that should be equal to local rate of change of density plus, because of this variation in density with respect to space, that convective rate of change of density, this fluid particles coming and going away from this, that information you come from there. So now you see, you can write, if I write this for the velocity, then it will be dv dt, where velocity will be vector, that will be equal to your acceleration, and I can write force is equal to mass into this acceleration, but that should be equal to your, if this is v, then v into this. Okay, so that will be your mass into this del v del t plus v dot del v. Okay, so now this operator is also called the total derivative. Yes.
Sir, you need to say del rho by del t, that means that the particle is increasing its size from itself. From something is increasing its size by time.
Yeah, del rho del t, it's not about the particle size, it is about the property density there is changing with time. That means in our aerospace, if we consider you are still in that fixed space, identified space, but the density, if the fluid might be expanding there or compressing there. Okay, so if it is expanding, okay, If you take a high pressure gas, you put in balloon and leave it, then it will expand. So that if it is expansion, then there is density will be changing. So that means locally there is a change in density. You see that? Okay. So now this is also called the total derivative, and that is, if I take this in the operator sense, if I write del del t plus v dot del, then that is a total density. Okay, a total derivative. So this total derivative we can write d rho dt in this fashion. You can write this, we wrote it in the cylindrical Cartesian coordinate. You can write this in the cylindrical coordinate, and you can see the differences between them. But when we talk about the acceleration of the fluid particle, then it will be this total derivative dv dt will be del v del t plus v dot del. So now when we write force is equal to mass into acceleration, then it will be mass into this acceleration, or mass per unit volume. If I take rho into dv dt, this will be rho into this quantity. Okay, that will be equal to summation of all the forces. That is the primary governing equation that we will see when we will be doing in the dynamics, and that you will be seeing in the fluid dynamics course. Okay, so if you write in Cartesian coordinate, you will see this, and I think we are about time, so I can take few questions and stop right now. Okay, you have classes. Some of you might not have classes at 1, no? So just give me a 1 minute. Okay, just allow me to discuss this thing. Yes, Ram, you have a question? Okay, so now suppose if you have a converging nozzle kind of shape, okay, and fluid is flowing. So you all know that is, if now this conservation of mass, this if it is incompressible flow we are talking, the fluid that is coming in with velocity u1 and it is going out with velocity u2. Let's say u1 is constant and u2 is also constant. I put a measuring probe here and measure velocity at point A. It is a steady flow. There is no change in velocity u1 and u2 with time. So there will be no change in velocity at A with time. So if my measured velocity v at A will be like this with time. So does it mean that this fluid, there is no acceleration of this fluid particle?
It depends on area.
Yeah, so now area is decreasing. So if area is decreasing, that we know that u1 is increased to u2, velocity has increased. So that means if the velocity is increasing, that means there has to be acceleration. Otherwise, how did velocity increase? So the fluid particle, as it is moving from here to here, the velocity is increasing. That means the fluid particle is accelerating. However, this with time, if I measure at a point, I will not catch this acceleration, because what you are measuring is del v del t. Okay, what you are measuring is del v del t. That means velocity at a location, fixed location, xyz is constant there. However, the acceleration will be corresponding to other term, that is this u del x, v del u del y, w del u del z term. Here it is only one directional flow, so u velocity is there. So you will have u del x at A. If you just calculate with respect to this, then it will be depending on this area. Okay, so v into A is constant, so based on that you will find out that it will depend on this, how area is changing with x. So this area change is creating a special rate of change in velocity at different point, and that is what will be the acceleration of the fluid particle here. Okay, so with this I stop here, unless you have a question. I see some question. Conductive acceleration. No, it is not conductive acceleration. It is called convective acceleration. Conduction, when you use the term conduction, is in heat transfer, that is related to the conduction in a stationary medium. So if you take a rod, one end is heated and other end is one end is connected with the heated body, then heat will flow in this direction as a conduction. But if you allow air to flow over this, then the heat will also transfer from this body, and that will be convection. So this is called convective acceleration. Okay, so because of the motion, The fluid particle are not at that same position, they are moving away. So because of the motion, this acceleration thing that you are seeing, so that's why it is called convective acceleration, okay, or convective rate of change of that property that we said. Okay, with this introduction, I will do little more of this introduction so that I can discuss some of the things that we are going to talk about, how the forces are generated and all, and more about the forces generated on an wings of an aircraft and all these things. Okay. So if you have any question, you can ask. Otherwise, I can stop here. Do you have any questions? So this recording will give me the attendance also at this point of time. Okay, so if there is no other question, then I will stop here and I will stop the recording. I don't know what it will do. So let me just stop this thing. It will automatically leave the program. Okay. So any other question? If not, then I'm ending today's class. So we'll meet again on Monday. Abhishek, I think you have to end the meeting. I am not able to end it for all. Abhishek, can you hear me? Abhishek, can you hear me? Okay, I think if all of us leave, then the meeting will automatically end.